TAs for this section won't be running office hours. The discussion section is after the exam. I'm guessing you guys won't really be there anywhere right after the exam. We'll be focused on grading so we can get those midterms back to you as soon as possible. The TAs are organizing a couple of review sessions early next week in addition to the normally scheduled discussion sections. So the best way to use these is if you take the practice exam, you should have all gotten a link to the practice exam last night. If you take that practice exam before coming to these review sessions, because at these review sessions, they'll be going through the problems in that practice exam in detail. So if you haven't tackled the problems before you get there, you're not going to get as much out of it. Just also generally talking about preparing for this midterm, what I'd suggest is obviously going through previous lecture slides to get a sense of content. On Monday, I'll also do a bit of a review of some of the major topics that we hit in the course. But in addition to looking at the lecture slides, I'd suggest going back over your old homework, taking a look at some of the sample solutions. You have sample solutions for homework 1 through 4. You'll get sample solutions for 5 over the weekend. Just going through that code, making sure you understand how it all works, would be a really good way to get ready for the exam. And again, with the practice exam, really try to take the practice exam in simulated exam conditions. You'll have 50 minutes, 50 minutes to take the exam in this class. So try to do that for the practice exam as well. In addition to the practice exam for this class, I've also put up some previous midterms that were from other sections of this class. They're also good practice with the types of problems you might have on the midterm. I'd suggest doing those after the practice exam for this class. And for those, there are already solutions up, so you can take a look at those solutions. One other related note, just based on a lot of the email and kind of responses that we've seen in office hours, many of you are not reading instructions very carefully. With all of these programming problems, both in this class and in the future when you're building real programs and real systems, it's very important to be detail-oriented. And in the course, we're giving you quite a bit of detail on how to approach the problems and many of the structures and ways of doing things that you should be trying. So just in general, be very detail-oriented. And when you're taking the exam, make sure you read all of the instructions before you start the problem. Obviously, midterm scheduling, and again, there are 2 rooms for midterm. You'll pick your room based on your last name. This will divide the class roughly in half, so you guys have enough space when you're taking midterm. Any questions? Yeah. The question is, will arrays be covered in the midterm? And we'll be covering everything up to the last lecture. So the last lecture included material on arrays, and today we're gonna talk about arrays a little more. But you should know all of the content of the last lecture. Today's lecture will reinforce some of that, and we'll move forward. Okay. Any other questions? All right, let's continue talking about arrays. So before we dive into some more material, I just wanted to do a little check over here. guys are split about approximately 50-50 between B and C. If you guys want to discuss, try to come to a consensus. If you remember from last lecture, if you initialize with fewer values, the extra values just get filled in with zeros. So the four elements of this array at this point are going to be 1, 2, 3, and 0. Now, when we get to the for loop, notice that this for loop is going from 1 to 3, and then exiting once I is equal to 4, right? And if you remember, array notation, when you're indexing into an array, it starts at 0. Right? So the first element is element 0. So we would skip over that element when we're doing this sum. And we sum over elements, the second, third, and fourth element, which have indices 1, 2, and 3. Right? And so we're going to skip over this 1. We'll add up 2, 3, and then 0 that got filled in. So that's how you get 5.
I'm still confused why you skip over
the 1. So indexing for arrays always starts at 0. So the first element is index 0. The last element is n minus 1, where n is the size of the array. So the last index into this array is going to be 3. Right? And values 3 is going to be equal to 0, that element that gets filled in. Values 0 is equal to 1. Any other questions?
So isn't that a character array?
Yeah, so that was, I did that on purpose, which is that characters, if you remember, are also integers, right? What makes characters special is that the values, or the numeric values of the characters map to printed characters. That was the ASCII table. The ASCII table shows you how to convert between the numeric representation that C knows that's under the hood, right? Maps between that and characters that are printed out. So a character can a car type can be both a number and a character, right? It represents both. And the way you use it will affect the interpretation. So if we had printed out, if we had done a printf, and we told it to treat values as characters, then it would be a very different interpretation. Right? It would be the ASCII table lookup. We'd look up 1, 2, and 3 in the ASCII table, and 0. We'll reinforce that when we start talking about string arrays, but that's a really important concept. If you go back to the lectures on data types, that should hopefully clarify. Any other questions? So let's move on. And last time we finished up our introduction, we showed some simple examples of using arrays. And today we'll get into some more complicated mathematical things. And if there's time, we'll introduce string arrays. So we left off with this slide last time. I wanted to remind you guys of how we did our decimal to binary conversion. Last time you saw this problem, we did it without arrays, and I wanted to just review that solution, and then we'll talk about a second solution that requires the use of arrays. So if you remember, in that first solution, we were going from left to right, printing out the higher significant binary digits and then the lower significant binary digits. And so if you look at the binary places, right, we can just put in their decimal value equivalents, right? So we go 1, 2, 4, 8, 16, and so on. Now, let's say we want to convert the number 10. The process was pretty simple. For each binary place, we just compared the number we wanted to convert with the value, and if this value is less than the binary place value, we put in a 0, right, because we don't need this bit. Obviously, if we included 32, the number would be 32 or higher. We don't need 16, but we need 8, right? So we put in a 1, and we subtract the 8 off of the 10, and we're left with 2, and so forth. And in previous lecture, you saw how you could implement this into code, and you didn't need arrays. So another solution to this problem was to fill in our binary representation, instead of from left to right, fill it in from right to left. And if we're filling in the binary representation from right to left, we need to store that representation so that we can print it out in the correct order. Right? And
I just had a question. Are there any situations in which switching from decimal to binary using arrays is more useful than
the question was, are there situations where converting using arrays could be more useful? Yeah, so if you needed to hold on to that binary representation to do some further decision making, you'd want to put it into an array, right? So when you saw this example, we were just spitting out the digits, the binary digits. We weren't storing them, so we couldn't manipulate them further. So that's why you might want to hold on to it in an array. So let's see how we can convert 10 into binary using this alternative method. And so the alternative method was just based on dividing by 2, right? The idea being that each one of these placeholders, each one of these digits increases by a factor of 2. So if we divide this number by 2, we can look at the remainder and figure out what these binary digits should be. So if we take 10, we divide it by 2, right? There's no remainder, so we didn't need the 1, right? And we're left with a quotient of 5. Now we have the same problem over again, but we need to fill in the next digit. So we divide by 2 again. This time there's a remainder, so we need a digit there. We need a 1 there, and so forth. Is it clear to you guys why this works? Okay, good. So let's look at how we implement that with arrays. So we'd start by declaring a variable decimal that's going to hold the user input, an array called bits that holds the actual bits that we print out. Now, when we declare this array, we obviously need to give it a size. We'll come back to that in a minute. Obviously, we want to take in what the user number is, right? What the decimal representation is, and then we just print that out. So based on this setup, how many elements do you think there should be in bits? What's a good answer there? So if you guys could click in. If you guys want to take a minute and talk to each other. Right now, the winning answers are B, C, and D. look in the next 15 seconds. Okay, so it turns out the right answer is C, or 32. And the way to see that, sorry, D, 32. D, mistake. The right answer is D, 32. And the way to see that is we're taking in an unsigned int, right, here. And if you remember, the unsigned int, an int as well, is represented by 32 bits, right? So the largest number that somebody could input here is a 32-bit number. So we want to be able to represent that in the rest of the code. Okay. So now that we have the correct size array and we have the number, let's go ahead and implement that divide remainder algorithm. So we use the do while loop. And the first thing we do in that do while loop is we set bits I, right? This is an I++, so the +1 is going to come after we complete this operation. So we're setting bits I equal to the remainder when we divide by 2, right? So decimal mod 2. So obviously this will be 0 if decimal is even, and 1 if it's odd, if there's a remainder in the division. And then we go ahead and we do an integer division of the decimal, right? And that's all we need within each iteration, but we need a way to figure out when to stop iterating, right? And the way we do that is, we check to see if decimal is non-zero. If it's non-zero, then this will be interpreted as true, and we'll keep looping, right? That means there's still more bits that need to be represented. If it's equal to 0, then we fully represented the number with I bits. And so we can go ahead and continue the program. Is that clear? Any questions? So then once we have decimal in this array of bits, we need to go back and print it out, right? And keep in mind, you want to print out from most significant binary digit to the least significant binary digit, right? And so the way we do that is we set up a while loop where we subtract off 1 from I. And the reason why we are proceeding here, if you remember here, in the final operation, we will have added 1 to I, right, before exiting. And so we know that that final placeholder, that final most significant digit, is definitely going to be 0, so we don't need to print it out. Right? Because it didn't get populated, right? We populated I, but not I++ in the iteration. And so now we subtract off 1. We check to make sure that I is not negative, right? Because we can't have negative places in our array. And for each entry going from most significant digit to least significant digit, we're going to print it out, right? We're going to print out the value in bits. And then finally, after we exit the while loop, print out the rest of our output in an end line. The reason why we're using unsigned int here is in this program we're only converting non-negative decimal numbers, right? So we could have used a signed int, right? If we use the signed int, what would happen is we would lose some of the range, right? So because a signed int has to represent both negative and positive numbers, so it can only represent half as many positive numbers. So by using an unsigned int, this program is capable of dealing with larger numbers.
Is there a way to just print out the array without, instead of just printing out the individual
elements. So what you would do is, when we talk about functions, you would likely write a function that gives you that capability. But for now, there isn't an easy way for me to show you how to do that. So hang on.
So the rest of the bits that weren't signed just have their random value in the system?
Yeah, correct. So the question was, the bits that don't get assigned by this program, do they just have random values? Yeah, so they're just going to have whatever was in memory before, because we didn't declare this array. We know that it's okay that we didn't initialize this array. We declared we didn't initialize it. We know it's okay because we've written the code carefully to make sure that we're only reading out from elements that we've written into, so we know what their values are. Any other questions? Yeah. So, now that you've seen this program, a question for you, which is, would it have been, which one of these representations would have been a better choice for representing, bits? Take another 15 seconds and just whatever you think is best. Okay, so let me just show you guys the results here. So B was the winner. Let's go through each one of these options and think about them. Between A, B, and C. So keep in mind, bits is just holding a 0 or a 1, right? So it can only take on those two values. And when you're choosing data types, you want to make sure that the data type can cover all of the instances you care about, but you also want to make sure that it's that it's efficient, that you're not taking up more memory than you need to, especially when you start defining arrays. The arrays can get very large. So here we were using an unsigned int to represent bits, but that's very wasteful because we're using 32 bits to represent 1 bit, or we're using a data type that can represent up to 0 to up to approximately 4 billion, when all we care about is 0 or 1, right? So it's very inefficient. So it'd be better to use something smaller. Now, some of you answered long int, and that goes in the wrong direction, right? A long int takes up 64 bits and can represent even larger numbers. So that would be a less efficient program. None of you answered floats or doubles. You can make this program work with a float or double. You'd have to change some of the printout commands to handle them appropriately, but it would be a poor choice because we obviously don't need real numbers here. Now, the car and the bool are both good choices from an efficiency standpoint. So both the car and the bool, their representations, if you remember from earlier lectures, take 1 byte. Right? They take 8 bits. So they're both equally efficient. The bool is a slightly better choice because the bool is meant to just take on true or false or 0 or 1 values. So in terms of your program being very readable, choosing the bool over the car would be better because it makes it very clear what that variable is doing. But from an efficiency standpoint, the two are equivalent. Any questions? Great, so let's move on to another math problem here. So here we're interested in calculating the median. And as you might recall, the median of the data set is a number that cuts the set in half. So half the data are above the median and half are below, right? So if you have a set of numbers that are input, to find the median, you might sort those numbers, and you would find a number that cuts this collection of numbers in half, right? So half of the numbers are less than 6, half of the numbers are greater than 6. So, by a definition is to arrange the n numbers in increasing order. Right? And here we're just taking our set of numbers and we've sorted them so that they follow the set of conditions. And we've some indices here. So each successive x here is greater than or equal to the previous one. Now, if n is odd, the total number of input, or the number of elements you input are odd, the median is simply the middle element of the ordered sequence, right? So it would be element x n plus 1, quantity n plus 1 divided by 2, right? That would be the middle of this sorted list. If n is even, then we have a special case, and the median is the average of the two middle elements. So that's just the mathematical definition of median. Right? So why do people use median? So it turns out that in some cases the median can be more useful than the average, right? So for example, in an exam scenario where there might be a very large range of scores, so some folks won't show up, here those zeros are not that useful for understanding the statistics of those that actually took the exam. So the average here would be very low, but wouldn't really be representative of the skill exemplified by those that took the exam. Whereas the median may be more. So how do we go about computing the median? So the most straightforward method from the definition that I showed you is to sort the n numbers into increasing order and then take the middle or the average of the middle two, depending on if you had an even or odd number of elements. This is a fine solution, but it does take some time. We won't go into detail about this, but if you have n numbers, it requires about n log n operations to sort them. And actually, if you're interested in learning more about these types of algorithms, there are algorithms classes you can take in the CS that will go into more detail. So it's not as efficient as we might want it to be. So there's an alternative method. And so this alternative method works when we know that the numbers can only take at most m values, right? So if we have integers that somebody is inputting and they're bounded, then the second method would apply because there's at most m values, a finite number of values each element can take on. So the way we calculate the median in that case is we make a histogram of the values observed. Making that histogram takes n operations, one operation per element that the person has put in. And then we can sum the histogram from left to right till the sum exceeds n over 2. Right? So once we hit that point where the sum exceeds n over 2, we'll know where the median is. And that summing operation takes at most m operations. So in certain cases, this method, the second method, can be more efficient. And that's why there are two methods that one would consider. But let's just focus in on the second method because we can make use of arrays to implement it. So the way to see that is, let's go ahead and set up a histogram. And here we're bounded in terms of our input values. The values can only go from 0 to 10 as integers. And let's say we have a set of numbers or elements that are being input, and we want to build that histogram. So the way we do that is we peel off these numbers one by one, and we would just add them to the right points in the histogram. We've seen 5 before, so we have another element there. We've seen 9 before, that's the second element, 7 before, 5 before, right? So we have 11 values, and the median will be the 6th value, right? That's the middle value when you have 11. So we just need to go ahead and sum up our histogram here. So obviously, we're at 0 for these first few sums. Then we get to 3, we add 1. Get to 4, add another one, we're at 2. We get to 5, we're going to add 3. Our sum is here at 5. We add this one, and we're at 6, right? And 6 exceeds n over 2, n was 11, so n over 2 is 5.5. So we know we can stop right here, and the median is going to be the histogram bin that we just looked at, right? Obviously, if you had an even number of values, you need to deal with that special condition slightly differently, right? We won't go into that in this example, but you should be able to, once we go through the code, you should be able to think about how you'd extend the program. So let's go ahead and formalize that. So let's compute that histogram. So let's say the input consists of 85 exam grades, each of which is an integer from 0 to 100. So to build that histogram, we obviously need to count the number of times each grade will occur. So we start off, we're using macros to hold the number of grades and the max grade. This allows us to easily modify the program if the number of students or the scoring metric changes. We start off our function here. So we need an array to capture the histogram. And so this histogram is going to have max grade plus 1 elements. The reason we need this plus 1 is because grades can range from 0 to max grade, right? So that would be max grade plus 1 total elements. And then we'll have a bookkeeping variable and a variable for inputting each successive grade, right? So then we have a for loop that's going to loop from 0 to n grades minus 1, right? So we're going to input a total of num grades. And so we're taking in the user input, and that input is going to be written to grade. And the way we implement our histogram, so note when we declared our histogram array, we also initialized it with a curly bracket notation. So that ensures that we have all zeros in our array. And so now what we can do is every time we see a grade, we can access the array element for that grade and just increment it. And once we've looped through all of the grades, we will have built our histogram. So we're going to slot in some additional code here for doing a median calculation. But once we do that, we can return. So let's take a look at how we're going to calculate the median. So again, in this program, we're going to assume that the number of grades is odd. And if your program makes such strict assumptions, it's very good to put in a comment up here where the user might, or where the programmer might change something. So here, since we're defining the number of grades up here, we want to make sure that if it's changed again, it's always odd, right? Otherwise, if you want to do an even number of grades, you'll have to change the program that follows. That's the program we have. So let's take a look at how that program works. So again, we're going to calculate that histogram just as I showed you in the last slide. And then we're going to go ahead and calculate the median. And we've introduced a new variable here, bar sum. And we're going to set both bar sum and grade equal to 0 to start. And what we'll do is we'll start a while loop here. And so this while loop is going to loop over, it's going to sum over the elements of num grades. And so what we're doing here is we're summing these guys up. So at each iteration, we're taking a look at the value in the histogram. So how many grades match grade plus plus, right? And I'm sorry, how many how many student scores match grade, right? We're gonna increment grade after we check that. So first, we look at this and say, okay, the value that we're accessing the array with is grade, right? We're gonna add one later. So we access that, we get the number of students that got that grade, we add that to var sum, then we increment grade, right? And so here, what we're doing is we're stopping this while loop as soon as this var sum exceeds the number of grades over 2, right? So that's the number of elements over 2. So that was our criterion for stopping, for when we knew we found the median. So we'll run that while loop until it stops, and then we can print out the median. And so note that when we print out the median, we have to subtract 1 from grade, right? Does anybody see why we have to do that?
Because you only break once grade has passed the median, so you have to then go back to the median.
Yeah, so what's happened is we've gone through this while loop, right? We've exceeded, but if you'll notice, we have this grade plus plus, right? So after we've done this var sum, we've already incremented grade up by 1 before checking this condition. So we've already moved over to the next bar, even though the next bar of our histogram, even though we haven't looked at it yet. So we just need to subtract off 1 to go back to the previous bar.
We're doing plus plus grade.